Imagine building a complete research report where each section writes itself in parallel, then automatically assembles into a polished final document, all with just a few lines of code. We'll implement an orchestrator-worker pattern where one LLM plans the report structure, multiple workers write different sections simultaneously, and a synthesizer combines everything into a finished product. You'll see how LangGraph's send API dynamically creates workers and manages their outputs in shared state. From LangGraph, types import send. #graph state. Class state type dict. Topic, SDR #report topic. Sections, list section #list of report sections. Completed sections, annotated. List operator add. #all workers write to this key in parallel. Final report, SDR #final report. #worker state. Class worker state type dict. Section. Completed sections, annotated list operator add. #nodes. Def orchestrator state. Orchestrator that generates a plan for the report. #generate queries. Report sections equals planner invoke. System message, content equals generate a plan for the report. Human message, content equals F, here is the report topic. State topic. Return sections, report sections. Def LLM call state, worker state. A worker writes a section of the report. #generate section. Section equals LLM, invoke. System message. Content equals, write a report section following the provided name and description. Include no preamble for each section. Use markdown formatting. Human message. Content equals F, here is the section name. State section, name and description. State section, description. #write the updated section to completed sections. Return completed sections, section content. Def synthesizer state. Synthesize full report from sections. #list of completed sections. Completed sections equals state completed sections. #format completed section to SDR to use as context for final sections. Completed report sections equals NNNN, join completed sections. Return final report, completed report sections. #conditional edge function to create LLM call workers that each write a section of the report. Def assign workers state. Assign a worker to each section in the plan. #kickoff section writing in parallel via send, API. Return send, LLM call, section S for S in state sections. #build workflow. Orchestrator-worker builder equals state graph, state. #add the nodes. Orchestrator-worker builder, add node. Orchestrator. Orchestrator-worker builder, add node. LLM call. Orchestrator-worker builder, add node. Synthesizer. #add edges to connect nodes. Orchestrator-worker builder, add edge start. Orchestrator-worker builder, add conditional edges. Orchestrator, assign workers, LLM call. Orchestrator-worker builder, add edge, LLM call, synthesizer. Orchestrator-worker builder, add edge, synthesizer, end. #compile the workflow. Orchestrator-worker equals orchestrator-worker builder compile. #show the workflow. Display image orchestrator-worker get graph. Draw mermaid PNG. #invoke. State equals orchestrator-worker invoke. Topic. Create a report on LLM scaling laws. From IPython, display import markdown. Markdown, state final report. This demonstrates the orchestrator-worker pattern, a powerful approach for decomposing complex tasks into parallelizable subtasks. The orchestrator acts as a central planner that breaks down a high-level goal into discrete work units, while specialized workers execute those units independently. What makes this distinctive is the clear separation between coordination logic and execution, enabling both parallel processing and dynamic task assignment. The pattern works through a declarative workflow where the orchestrator first generates a structured plan, then dynamically spawns workers for each subtask using LangGraph's Send API. Workers operate on isolated state slices, but write results to a shared output key, allowing the orchestrator to later synthesize all contributions. This design enables true parallelism while maintaining a clean boundary between task decomposition and execution, with the graph structure handling all coordination implicitly. This approach shines for document generation, multi-step analysis, or any workflow where subtasks have clear boundaries but variable execution paths. It solves the dual problems of sequential bottlenecks and rigid workflows by enabling dynamic parallelism without manual thread management. The trade-off is slightly higher initial complexity in defining the graph structure, but the payoff comes in scalability and maintainability for nonlinear workflows. Let's break it down. From LangGraph, types import send. Imports send from LangGraph, the core mechanism for parallel node execution. This enables dynamic routing where one node can trigger multiple worker nodes simultaneously. Hash graph state. Class state typed dict. Topic, SDR hash report topic. Sections, list section hash list of report sections. Completed sections, annotated. List operator add. Hash all workers write to this key in parallel. Final report, SDR hash final report. This defines the graph state schema using typed dict, where each key represents a stage in the workflow. The completed sections field uses annotated list operator add to enable parallel writes from multiple workers, automatically merging their outputs. This pattern ensures thread-safe accumulation of results without race conditions. Hash worker state. Class worker state, typed dict. Section. Completed sections, annotated list operator add. The worker state defines the isolated state for each parallel LLM call worker. It carries the specific section to process name description and uses annotated list operator add on completed sections to safely merge individual section outputs into the shared state completed sections list when workers return. This lets each worker append its generated content without overwriting others. Def orchestrator state. Orchestrator that generates a plan for the report. Report sections equals planner invoke. The orchestrator node takes the initial topic from the graph state and invokes the structured output planner, LLM, configured with a sections schema to generate a list of report sections. This output drives the parallel LLM call workers, with each worker processing one section from the returned sections list. The node updates the state by writing the generated sections to state sections. Def LLM call state, worker state. A worker writes a section of the report. Section equals LLM, invoke. This defines the worker function that generates individual report sections. It takes a worker state containing a single section's metadata, then uses the LLM to write that specific section in isolation. The parallel execution pattern enables concurrent section writing for faster report generation. Hash write the updated section to completed sections. Return completed sections, section content. This returns the completed section content wrapped in the state's completed sections key. The list wrapper enables parallel writes from multiple workers, as LangGraph's annotated list operator add
Reducer merges all worker outputs into a single list.
Def synthesizer state. Synthesize full report from sections. Completed sections equals state completed sections. Completed report sections equals NNNN. Join completed sections.
This is the report assembly function. It takes all completed sections from parallel workers and combines them into a single document using Markdown horizontal rules as separators. The join operation handles the parallel to serial conversion, merging worker outputs into the final report structure.
Hash conditional edge function to create LLM call workers that each write a section of the report. Def assign workers state. Assign a worker to each section in the plan. Hash kickoff section writing in parallel via send, API. Return send, LLM call, section S for S in state sections.
This is a dynamic parallel task dispatcher. It creates one LLM call worker per report section, enabling concurrent section writing. The send API here implements fan-out parallelism, where each section gets processed independently before merging in the synthesizer.
Hash build workflow. Orchestrator-worker builder equals state graph, state.
This initializes the workflow graph using LangGraph's state graph class, binding it to our state type. This establishes the execution framework, where nodes represent processing steps and edges define the data flow between them, enabling the parallel section writing we need for report generation.
Orchestrator-worker builder, add node. Orchestrator. Orchestrator-worker builder, add node. LLM call.
Registers the two core processing nodes in the workflow graph. The orchestrator node handles initial report planning by generating section requirements, while LLM call nodes execute the parallel section writing tasks. This separation enables the pipeline's first phase, planning, to trigger multiple concurrent workers for the second phase, execution.
Hash add edges to connect nodes. Orchestrator-worker builder, add edge start, orchestrator.
This establishes the workflow's entry point by connecting the start node to the orchestrator node. It ensures execution begins with the orchestrator function, which generates the report plan before any parallel processing occurs.
Orchestrator-worker builder add conditional edges. Orchestrator, assign workers, LLM call.
This creates dynamic parallel execution. The conditional edge uses assign workers to generate multiple LLM call tasks, one per report section, enabling concurrent section writing. This pattern efficiently distributes work without manual thread management.
Orchestrator-worker builder, add edge, LLM call, synthesizer. Orchestrator-worker builder, add edge, synthesizer, end.
These edges define the workflow's final processing pipeline. After all parallel LLM call workers complete their sections, the graph routes to synthesizer to combine results into the final report. The subsequent edge to end terminates the workflow, ensuring clean completion after synthesis.
Hash compile the workflow. Orchestrator-worker equals orchestrator-worker builder compile.
This compiles the graph definition into an executable workflow. The compilation step validates all nodes and edges, optimizes the execution path, and creates the runtime instance that will process the state transitions. Without this, the graph remains just a blueprint compilation, makes it operational.
Hash show the workflow. Display image orchestrator-worker get graph. Draw mermaid PNG.
This visualizes the workflow graph using mermaid diagram rendering. The Draw Mermaid PNG method generates a graphical representation of the state transitions, making it easier to debug and understand the parallel execution paths between orchestrator, workers, and synthesizer.
Hash invoke. State equals orchestrator-worker invoke. Topic. Create a report on LLM scaling laws.
This triggers the compiled workflow with the initial topic. The invoke method executes the entire graph from start to finish, processing LLM scaling laws through the orchestrator, parallel workers, and synthesizer to generate the final report.
From IPython, display import Markdown. Markdown, state final report.
This renders the final report as formatted Markdown in the notebook output. The IPython display Markdown class converts raw Markdown text into properly rendered content, making the report readable with headers, lists, and other Markdown formatting preserved. Parallel orchestration pattern. This implementation demonstrates LangGraph's orchestrator-worker architecture, where the send API dynamically spawns parallel workers for each report section while maintaining shared state through annotated collections. The completed sections list uses operator-add for thread-safe aggregation, which silently handles concurrent writes, but requires all workers to return list-wrapped content. Master this pattern to decompose complex workflows into parallelizable units while preserving deterministic state management.
The section that divides the whole unites the work.